Within 10 years, the job you are training for may still exist, but the world you're trained to work in will feel completely different because nature won't stay safely distant. The unsettling part isn't that storms, heat, or ecosystems change. It's that those changes will become measurable, predictable, and operational in near real time, like utilities. If you can't read that signal, you'll be planning with yesterday's weather, yesterday's risk, and yesterday's supply chain. Here's what's shifting. Sensors are spreading everywhere, and they're getting cheaper, smaller, and more connected. That means rivers, forests, coastlines, and even soil moisture aren't just being studied after the fact. They're being monitored continuously, streaming data that updates as conditions evolve. Now, add satellites that can see temperature, vegetation health, and land change patterns from space, plus drones and ground stations that fill in the details where space data can't reach. The result is a live map of nature's state, not a one-time report. And that live map is becoming infrastructure. In plain terms, it works like this. Data flows into models that translate raw measurements into actionable forecasts where the next drought stress will hit, how quickly a wildfire fuel load is building, or which regions are sliding toward crop loss. Those forecasts then plug into real systems: insurance pricing, emergency dispatch, logistics routing, agriculture scheduling, and building design. Nature data stops being environmental information and becomes operational input. This is why nature won't feel far away. When the atmosphere, ocean, and biosphere are monitored like a connected network, every delay becomes expensive. Farmers can't wait weeks to learn soil conditions. Port operators can't gamble on wind shifts. City managers can't treat floods as rare surprises. The companies that act on real-time ecological signals will move faster, waste less, and recover sooner. The ones that ignore will be stuck reacting to damage while everyone else is already rerouting, replanting, or rebuilding smarter. The most incredible fact is that the nature layer is turning into something like a dashboard for the planet. Not because we're controlling the Earth, but because we're finally measuring it at the speed nature changes. And if you're wondering whether this will stay the domain of scientists, think again. The interfaces are moving toward consumer-level simplicity dashboards, alerts, and decision tools that fit into everyday workflows. When reality becomes the live feed, you don't just hear about risk. You feel it on time in your decisions. So here's the question that matters right now. What will your life look like when nature itself is not the background of your day, but the real-time system driving it? One within a decade. Climate control won't sound like a government program or a lab experiment. It will sound like a calibration loop fed by microbes. And the unsettling part is that the biggest lever of greenhouse gases isn't factories. It's living communities so small you'd miss them with the naked eye. Microbes are everywhere, in soil, in ocean water, and in the guts of animals. They break down organic matter, and in the process, they either release or consume key climate gases. Some microbial pathways emit carbon dioxide and methane, while others pull carbon into stable forms. The balance is sensitive to temperature, oxygen levels, nutrient availability, and moisture. In other words, the microbial engine doesn't just respond to climate, it helps regulate it, locally and globally, one layer at a time. What has changed is that sensing and modeling are finally catching up to this biology. Sensors can now measure gases and chemical signatures at higher frequency, not just once a season. So instead of estimating microbial activity from broad averages, researchers and operators can infer what's happening in near real time. Modeling turns those signals into mechanistic predictions, translating patterns into forecasts of how carbon and methane fluxes may shift as conditions change. This is becoming climate control intelligence because the loop is operational. You don't just watch the atmosphere. You track the processes that generate it. When temperature rises or oxygen drops in a region, microbial communities reorganize, and the emissions profile changes. With rapid measurements and fast models, the system can anticipate that shift rather than document it after the damage. Agriculture is the first obvious battleground. Soil is a microbial habitat, and management choices, fertilizer type, irrigation timing, Crop residues restructure microbial activity. Precision farming is evolving from yield optimization to carbon-aware decision-making, using ecological signals to reduce methane and improve soil carbon storage without sacrificing productivity. In marine environments, monitoring helps predict when microbial conditions favor methane release or when oxygen-rich regimes suppress it. Meanwhile, policymakers and insurers benefit too, because microbial-driven feedbacks can change the timeline of risk. Floods don't just wash over land. They change soil oxygen and nutrient chemistry, which can amplify greenhouse gas emissions in the aftermath. Better biosphere sensing reduces blind spots in climate projections and improves planning for everything from carbon markets to resilience investment. So when you hear nature is the climate engine, remember, it's not only forests and ice. It's the microbial world doing invisible work at molecular speed. And if those communities can be measured, inferred, and modeled as an always-on system, then the next disruption isn't scientific, it's practical. The future question is whether your industry will treat microbes as a background variable or as a real-time control signal that determines what happens next. Forests are not static cathedrals of wood. Within a living landscape, they behave more like adaptive networks that reroute survival strategies as conditions change. Trees don't talk like humans, but they communicate constantly using chemistry, electrical signals, and the timing of growth. When a branch is damaged or attacked, nearby trees can respond sometimes faster than you'd expect by shifting their sap chemistry and producing defensive compounds. A key part of this system is underground. Many forests are threaded together by fungi. Through fungal networks, trees can trade resources such as sugars, water, and nutrients, especially phosphorus and nitrogen. In plain terms, the mycorrhizal web acts like a shared supply line and a distributed delivery system, redistributing what each tree has in abundance to the neighbors that need it most. Stress is not just endured, it's processed. Drought, heat waves, insect outbreaks, and nutrient shortages all trigger physiological decisions at the tree-level changes in stomata opening, growth patterns, and hormone signaling. Those signals travel through the network, so the forest can prioritize recovery where it matters. That's why two areas of the same forest can look identical on the surface, yet recover differently. The invisible signals and resource flows were different from the start. The newest twist is that forest cognition is becoming measurable. Imaging tools can track subtle changes in water movement, leaf chemistry, and electrical activity. On top of that, AI models can infer patterns from messy, real-world signals, learning how networks shift when stress rises, and predicting which trees are likely to sacrifice growth to keep the system stable. Instead of guessing, researchers can correlate signal signatures with recovery outcomes, almost like turning plant physiology into a data language. When you combine high-resolution sensors with machine learning, the forest starts to look less like a collection of individuals and more like a coordinated, resilient system. Not conscious in the human sense, but adaptive in a way that resembles computation. Observe, respond, reroute, and stabilize. And that's the part that should make leaders sit up. If forests are networked and responsive, then deforestation, fragmentation, and climate shocks aren't just removing trees, they're cutting communication channels and breaking the feedback loops that support regrowth. So as sensing gets cheaper and models get smarter, the next question becomes urgent. When we can monitor a forest's signals, will we manage it like infrastructure or watch it fail like a static background? Oceans don't just absorb heat. They regulate it by changing the chemistry of seawater and the routes that water takes. The key idea is chemical switching. As the planet warms, the ocean alters how much salt, nutrients, oxygen, and carbon dioxide it can hold, and how easily it moves those components around. When surface waters heat up and freshen from melting ice and heavier rainfall, the density pattern shifts. That density controls circulation, meaning the mixing system slows down in some regions and speeds up in others, like turning a dial on how heat is distributed. In plain terms, warmer oceans push currents to behave differently, and different currents carry different chemical properties. That matters because carbon dioxide doesn't just float around, it reacts. In warmer, less well-mixed waters, CO2 can build up near the surface, while deeper layers may struggle to exchange gases. The ocean's ability to trap or release heat then changes, because heat is carried both by water movement and by the chemistry that governs how energy is partitioned. To now add ocean acidification and oxygen decline into the equation. As more CO2 dissolves, seawater becomes more acidic, which can stress shell-forming organisms and entire food webs. Oxygen drops when warm water holds less oxygen and when circulation can't replenish it as efficiently. These shifts are not immediate across the globe, but they cascade through biology, which in turn affects chemistry. Because living ecosystems influence carbon and nutrients, it becomes a feedback loop. Chemistry changes the ecosystem, and the ecosystem changes the chemistry. What's accelerating this is continuous measurement. Traditional ocean sampling is powerful, but it's slow. Ships, buoys, and occasional satellite snapshots. Today, dense networks of sensors, some moored, some drifting, some mounted on autonomous gliders, measure temperature, salinity, oxygen, pH, and currents in near real time. Even better, they capture transition signatures, the small inflection points when the ocean switches modes from stable mixing to sluggish exchange. One machine learning then stitches the data into forecasts. Instead of asking only, how warm is the ocean today? Models ask, how is the ocean's chemical behavior likely to evolve within the next few weeks of wind, rainfall, and current anomalies? They learn correlations between circulation patterns and chemical outcomes. So forecasts improve faster than climate models alone, especially for regional impacts. Two, the disruption for society is immediate, not theoretical. Fisheries, shipping routes, coastal protection planning, and disaster preparedness depend on knowing how quickly heat and chemical stress will build. When forecasts become more responsive, interventions can shift from reacting after damage to anticipating where conditions will tip, like predicting which coastal areas will face low oxygen events sooner, and which regions will sequester or release carbon differently. Two, and once you realize the ocean is switching chemistry continuously, the question becomes personal. When your coastal community or business plan relies on typical ocean conditions, what happens when the baseline moves faster than your policy cycle can? Nature isn't just changing its running dynamic chemistry. And oceans are the clearest proof. Feedback loops, rapid sensing, and forecasts that can spot tipping points before they become disasters. The takeaway is simple. The future of resilience depends on measurements, not assumptions. And planning must move at sensor speed. If you're building a strategy for business, policy, or your community, audit your typical assumptions and start tracking real-time indicators now. Subscribe to Future Vision Insights and share this with someone who needs to prepare earlier than they think.